Hello and welcome to our lesson on factors and roots of polynomials. So in the previous lesson, in the previous topic, we talked about division, the different ways that we can divide. Those were the quotient rule, synthetic division, and then long division. And we talked about if a polynomial divides evenly into another, then that polynomial would be a factor of the other. Now, why is that important is part of what we're going to be discussing today. So we're going to talk a little more about factors, why it's important to know if a polynomial is a factor of another, and then we're going to try to connect that to roots. Okay? So recall, if a polynomial, we said, oops, that's my highlighter, sorry. If a polynomial divides evenly into another polynomial, then it is a factor of that polynomial. So if we divide and we get a remainder of 0, then it is a factor. And why are factors important? So we've talked about this previously in our quadratic module, but just to reinforce, if we had a polynomial expression like x squared plus 5x plus 4, if we were to factor that using bottoms up, we end up factoring into x plus 1, x plus 4. But when it's in an expression format, factoring is just a way to rewrite that expression, but it doesn't really do much for us. The expression in either format, whatever, it is what it is. But if we take our expression and we make it an equation equal to 0, well, then that factored form is helpful. So I can't see the solutions to this equation when I'm looking at it in the standard form, but in factored form, I can see right away that one of my solutions is -1 and that my second solution is -4. So as an expression, the factored form doesn't do much for us, but as an equation, the factored form helps us identify the solutions. And sometimes it's literally as easy as looking at those factors and identifying those solutions. And then when we're looking at the related function. So here's our expression. We would call this the related equation. This would be the related function where the actual x squared plus 5x plus 4, that piece of it is the same. So this makes it a function, this makes this an equation, and then the fact that there is no equal sign on the other makes an expression. But those are all related, okay? So factoring for the sake of factoring with an expression, not helpful. When we're looking at an equation, we know exactly the solutions to that equation. And then when we're looking at a function, those solutions are the same, but what they are in terms of a function is where your graph crosses the x-axis. They are the roots. Because when you're looking for an x-intercept, you put a 0 in here for y. And if you were to put a 0 in here for y, you end up with the same equation that we had here. So then our solutions at x equals -1 and x equals -4 are really roots. When x is -1, our y value is 0, and when x is -4, our y value is 0. So the factors are important because the factors show us the solutions to our equations, and they show us the roots to our functions, which happen to be the same x values. Okay, so factors reveal the solutions to our polynomial equations, which also happen to be the x-intercepts or roots of our related function. Or remember, we could also call those zeros. So x-intercepts, roots, zeros, all interchangeable there. Okay? X-intercepts, zeros, roots, solutions, all interchangeable. All right, so what types of problems should we be able to solve with this knowledge? So the first question says, identify the roots of the following function. So if it says identify the roots, that means it's asking where is this graph crossing the x-axis? Well, of course, I have technology that can graph this for me. If I put in my x and x minus 7 and x plus 2, sorry, I'm a little slow here, and 3x plus 1. It's because my fingers are fat and this keyboard is small, okay? Alright, so here's my function. If I wanted to know the roots, there they are. Where is this graph crossing the x-axis? At -2, at -0.3 repeating, at 0, and at 7. Now, that didn't take much work, but it really shouldn't have taken any work at all, because the roots we can see from the factors. So this out here, x has to equal 0, think about this as an equation, okay? If we were trying to zero out our equation, 0 would have to be a solution, okay? Or here, x would have to equal 7 if this thing was zeroed out. Or here, x would have to equal -2. And then here, x would have to equal a -1/3. Those are the same roots we saw there. So those solutions, if we were to zero out this equation, tell us that we would have roots at 0, 0, at 7, 0, at -2, 0, and at -1/3, 0. Okay, now this one gives me the decimal format here. Oops, geez, come on. This one gives me the decimal, but if you needed to convert -0.3333 repeating, if you just put that in there a whole bunch of times, and then hit your fraction button, it will turn it into a fraction for you. Although I would argue that you should know that 0.3 repeating is 1/3 as a fraction because it's occurred enough times. But there it is. So you should be able to find the roots of a function, any function, and you can obviously use technology, but if it's in factored form, you should be able to look at it and establish where the roots are going to be. Okay, and you should also be able to work backwards. So if you have your equation in standard form like we do, or your function in standard form like we do in number 2, we should be able to write it in factored form. Now, if I said to, sorry, let me go back. It says to write the following polynomial function in factored form. If I said to factor this, right now the only, well, right now, forever, the only way we know, the only method we can use to factor a polynomial with 4 terms is grouping. But if we tried to group this, x squared would come out here, leaving you 5x plus 18, and only a -1 would come out here. And so grouping is not going to work because we don't have a common binomial. So the only method we know for factoring doesn't actually factor here. That doesn't mean that this polynomial doesn't factor, it's just we can't factor it using our traditional methods. So how do we use what we know about roots to make this in factored form? Well, in the same way the factors show me the roots, if I can find the roots, then I know the factors. So I'm going to go to my calculator again, and I'm going to put this function in and find the roots. So 5x to the third, and then we're going to add 18x squared. We're going to subtract 11x, and then we're going to subtract 12, and we're going to see that this function is going to touch the x-axis 3 times. So we have roots. So we graphed in Desmos. To find roots at -4, 0, -0.6, 0, and 1, 0. Okay, so, and just to be clear, I think we've talked about this before, but how do I know to stop with those 3 roots? How do I know there will only be 3 roots here, or 3 solutions if this were an equation? If you recall, the degree is what dictates how many solutions we could have, which would then in turn be how many roots we could have. Because this has a degree of 3, I'm looking for 3 possible solutions or roots there. If we had a degree of 4, like we do in the last one, we've got x to the 1, 2, 3, 4th all together, then it's 1, 2, 3, 4 roots or solutions. So the degree of our polynomial is what's dictating how many solutions we could have. All right, so let me go back here. How do I use these to now write this function in factored form? So f of x is going to equal, if -4 is a root or was a solution to the equation, the related equation, then x plus 4 had to be a factor. Now the decimal one there is tricky. The fraction is going to be a little more helpful. 0.6 as a fraction is 3/5, and let's put that over here. 0.6 as a -0.6 decimal as a fraction is, I meant to stick that negative in there, sorry. -0.6 is equal to -3/5. So what would make that as a solution would have to be a 5x and a plus 3. So remember, division by 5 means there has to be multiplied by 5, and then the minus 3 means there has to be a plus 3 here. Or use the bottoms up, but remember, we've got to put the opposites into our roots. Okay, and then lastly here, if 1 was a solution or a root, then x minus that 1 had to be a factor. So we should be able to identify the roots by looking at the function. We should also be able to write a function in factored form by finding its roots. Okay, so use the roots, or use the factors to find the roots, or use the roots to write the factors. That's what we did in 1 and 2. All right, how about number 3 is an interesting problem. It says, Bernice was trying to write the following polynomial function in factored form, like we just did in the previous problem. She used her calculator and was only able to find 2 of the roots. Since she couldn't find the third, she couldn't finish factoring. So she knows there's an x plus 4, or an x plus 5 and x minus 4, doesn't know what the last factor is because she doesn't know what the last root is. So let's go ahead and put this in the calculator. Maybe she's just silly and couldn't see it. Let's see, x to the third, and then minus 61x squared minus 82x plus 1,240. Well, there they are. There's her 2 roots, and I don't know how far we'd have to go with this, but there they are, the 2 roots, okay? Now, there's got to be a third one, and I know there's got to be a third solution here because there's a degree of 3. So the question is, how do we figure out what that third one is if it's not appearing on our calculator? So if you recall, if x plus 5, for instance, is a factor, or x minus 4 is a factor, we know that it divides evenly into our function. So let me show you with some numbers real quick. So if I had, let's say 30, and I said 30 was equal to 2 times 3 times some number. So I broke it down into 2 of the factors, but I just needed the third one that was missing. What would I do? Well, the 2 and the 3 make 6 here, so 6 times some unknown number has to be 30. What would I do? Well, I could divide that over, right? If I divide that over, then I'm going to know that my remaining factor had to be a 5. Now, it's not as simple, the division here, but I could divide the 2 over first, right? Let me look at this one here. If I divided the 2 over first, then I could say that 15 is equal to 3 times my number, and then I could go ahead and divide the 3 over and say, again, that my missing number had to be a 5. So that's the approach we want to take with this problem here. I know 2 of the factors. If I divide both of those out, I should be able to find that missing factor. And because what we're going to divide by, these are of the form 1x to the first plus some number, we can use synthetic division. So we're going to divide f of x by x plus 5, then divide the result can't spell. The result by x minus 4, and that should give us our remaining factor. So we're going to start by putting a negative 5. The opposite of this number would be a negative 5 outside of our division box. That is going to be upside down for synthetic division. And then we're going to put in our coefficient of 1, and then negative 61, negative 82, and then 1,240. And now let's do our synthetic division here. So we start by bringing down our first number, and then remember it's multiplying and then adding until we get to the end. And we know at the end here we should have a remainder of 0 because we already know that x plus 5 is a factor. So if we don't get a 0, then we know we screwed something up. Okay? So negative 5 times 1 is negative 5. If we add these, we get negative 66. And then we're going to multiply negative 5 times negative 66. 66 times 5 is going to be 330. So 330 here, and then we're going to add. So 330 minus 82 is going to give us 248. And then we're going to multiply that by negative 5. times a negative 5, and we're going to get negative 1,240. Good, because those should 0, giving me no remainder. So I divided by the first factor. Now I'm going to take this result and divide by the next factor. So I'm going to divide by the next factor, this minus 4. So I'm going to divide by a plus 4 outside of this box. And again, I should get a remainder of 0. So I'm going to bring the 1 down. And 4 times 1 is 4. I'm going to add here, which is going to give me a negative 62. And then I'm going to multiply. I'm going to get a negative 248. And then that's going to 0 out. So what is it that we have left here? Remember, we started with an x cubed. We divided it down to an x squared. And now I have an x to the first as my result. So this is telling me that x minus 62 is my last factor for this function, which means positive 62 is my last solution. So the remaining factor is x minus 62, and the remaining solution was 62. Solution was x equals 62, or the remaining root. There's so many different ways to say this because they're all connected. We could say let's turn the pen on. The remaining root is at 62 and 0. And I suppose that is why we didn't see that on the calculator. Let me see. Let me get my function back in here. There it was. I suppose if we zoom out a little, yep, there it is. Just didn't zoom out far enough. And now if you weren't using Desmos, if you were actually using a graphing calculator, it would have a really hard time calculating a root that far out. With Desmos, we're fortunate that we can zoom pretty easily, but now we can confirm that 62 was in fact the remaining root. Okay, but division is a skill you should have. So a couple more things you need to know about roots, and that is, like I mentioned earlier, the total number of solutions is, or the total number of roots is determined by the degree. Okay, so if you have a fourth degree, you should have 4 solutions. Fourth degree equation, 4 solutions. Fifth degree equation, 5 solutions. Third degree equation, 3 solutions. Now, some of those solutions don't necessarily appear on our graph. Remember, if we had a quadratic that had imaginary solutions, it wouldn't actually touch the x-axis. So what do we do in that case? Or how we find those imaginaries is something that we're going to talk about in the near future. But for now, what has to be true about those imaginary roots or those complex roots, or even our irrational roots, is that they have to come in pairs. So let me just deviate for a second here. So if you have an imaginary root, let's say you were solving x squared equals negative 25. If you were solving this, you would be taking the square root of both sides, and you would say x is equal to plus or minus 5, and then the negative becomes imaginary, right? So you have 2 imaginary solutions there. Or if you were solving, if you were solving x plus 1 squared equal to, let's go, negative 16, then you would do the same thing. You would square root both sides, and you would say x plus 1 equals plus or minus 4i, but this time you would have to subtract the 1 over, and since it's not a like term, you'd have negative 1 and plus or minus 4i as a separate term. So now you have 2 solutions, but this time they're complex. So these are imaginary. These are complex. And then maybe you get something like x squared equal to 8, where when you go to square root both sides, x is going to equal plus or minus, this breaks down to 2 radical 2. And these solutions are, so this is 2 imaginary, this was 2 complex, and this was 2. This would be our irrational solutions. Okay, now something is true about all of these situations. The only time we ended up with With the one solution, remember, for our quadratics was when we had the 0 under the square root. But in any other case, we ended up with the two solutions. It's always going to be true if you have an imaginary solution, a complex solution, or an irrational solution. Those will come in pairs. So you can't have just one imaginary solution. You can't have just one complex solution. You can't have just one irrational solution. It's not possible. Because every time they occur when you take the square root. Right? Every time you take the square root, you're going to have that plus or minus in there, and it becomes imaginary because the negative is underneath. So that plus or minus happens every time you take the square root. So if positive 5i was a solution, negative 5i, its partner had to be there too. Or if negative 1 plus 4i was a solution, negative 1 minus 4i had to be a solution as well. So they come in pairs, right? If 2 radical 2 is a solution, negative 2 radical 2 had to be a solution as well. Because every time you're taking the square root of that negative, okay, or that imperfect square, you're going to get plus or minus this pair of things. So our imaginary, complex, and irrationals always come in pairs. So all imaginary, can I go back to blue so this is a little more uniform? All imaginary, you like how I talk to myself, right? Sorry, complex, remember we can sort of identify those the same way, and irrational solutions, they all come in pairs. Okay? So for example, on number 4, if a polynomial of degree 3, that's important, that tells us 3 solutions, okay? If it has roots or solutions of x equals 3 and then 2i, what does the remaining root have to be? So x equals 3 is one of our roots, and then let me just list these out. So they gave us x equals 3, and they gave us x equals 2i. What is the remaining root? Remember, these imaginaries have to come in pairs. If 2i was a solution, then negative 2i had to be a solution as well. So that is our remaining root. And that would give us 1, 2, 3 total that we were supposed to have. Okay? So then the same thing here. If you have a polynomial function of degree 7, okay, it says we have a root at x equals 3. That's rational. That's not going to have a pair. It says x equals 1 plus 4i. And then it says x equals negative 2i. And also we have x equal to a negative radical 2. So right now we have 4 solutions. The irrational, the imaginary, the complex, that's what these guys are. We have imaginary, complex, irrational. Those come in pairs. Those all have a partner. Rationals will not. So there's 4 solutions. We are missing 3. So the remaining roots come from this one. Its pair would be 1 minus 4i. Remember, the plus or minus would have went right there. Okay. And then if negative 2i is a solution, then positive 2i had to be a solution. Remember, plus or minus would have been there. And then if negative radical 2 was a solution, then positive radical 2 would have had to have been a solution as well. So remember, plus or minus would have been in right there. So now we've got 1, 2, 3, 4, 5, 6, 7 all together. So those are our 3 remaining roots or solutions. Okay? So now, what can we do with this? Well, we can technically write our functions if we know the roots. So for example, in number 6, it says to write a polynomial function of degree 3 in factored form, degree 3, 3 solutions, and we know that one of them is x equals 1. We know another one is x equals radical 5. And then even though it doesn't tell us, we know those come in pairs, so our third one has to be a negative radical 5. So that means our function, f of x, in factored form, write this over here, in factored form, if 1 is a solution, here, let me color code this a little bit better. X equals radical 5. So if 1 is a solution, that means that x minus 1 had to be a factor. If radical 5 is a solution, we could say x minus radical 5 is a factor. And then if negative radical 5 is a solution, we could say x plus radical 5 is a factor. And that could be our factored form. Now, some teachers don't like to leave this piece of the function this way because we don't typically factor with radicals. So if you wanted to multiply this out and call it x squared minus 5 as a factor and x minus 1 as a factor, that would be totally fine as well. But I'm really okay with the radicals being in there as factors. My thing is I want you to understand that the opposite of the root goes into the factor, and that these complex imaginaries and irrationals come in pairs. Okay, so there's the factored form. The harder part would be taking this and putting it into standard form. So writing an equation, again, degree 3 this time, in standard form. That means we're going to have to multiply this out. It says x equals negative 4 is a solution. It says x equals 2 radical 3. And so its partner, the missing, would be a negative 2 radical 3. So there's our 3 solutions. So now our function, f of x, in factored form is going to be, let's see, x plus 4, right? Opposite of negative 4 is positive 4. And then pink, x minus 2 radical 3. And then lastly, x plus 2 radical 3. So that's the factored form. Now I have to multiply that out to get standard form. Now it doesn't matter which order we multiply, but I would start by multiplying the conjugates because the middle terms are going to cancel. So if I multiply out these conjugates, I'm going to end up with an x squared, a 2x radical 3, 2x radical 3, and a negative 2x radical 3 that will cancel. And then at the end here, a negative 4 radical 9. So again, these cancel. That gives me x squared and then negative 4 times 3. Radical 9 is 3, right? But negative 4 times 3 is 12. So this is just going to be x squared minus 12. Okay, so this these conjugates become x squared minus 12, but I still have to multiply that by x plus 4. So I have to make sure not to lose that piece. So now it's one more round of multiplying. Do I have any more colors? Alright, let's try this one. So we have x times x squared, which is x cubed, and then x times negative 12, which is negative 12x, 4 times x squared, which is a positive 4x squared, and then 4 times negative 12, which is a negative 48. So our standard form, we're going to say f of x is going to be equal to x cubed plus 4x squared minus 12x minus 48. And there it is. That is our standard form. Okay? So hopefully that wasn't too terrible. Just got to recognize the connections between the roots and the solutions and the factors, and know that the complex imaginary and irrational roots solutions, those come in pairs. Okay? So you've got some practice to work on. Give it a shot. But as always, if you need some extra help, just reach out. All right, guys, take care.